Again, very welcome to the quantum physics by Bhartiya Kisan, Bhartiya Farmer or Bhartiya Krishaks. And think you are enjoying my lecture very nicely. And today's topic is diffraction of electrons using Bragg's analysis. Using Bragg's analysis, analysis developed for X-ray scattering and the angle of scattering at which the pronounced peaks were produced, they calculated the wavelength of electron waves. They finally found very good agreement between their values of wavelength and those predicted by de Broglie hypothesis. Thus, the validity of the de Broglie hypothesis was established. In one particular experiment, the electron beam was accelerated to a potential of 54 volts and the maximum intensity was observed at an angle of 65 degree between a particular family of crystal planes and the incident beam, that is a scattered beam. Incident means a scattered beam. The spacing between the crystal planes as measured by X-ray diffraction techniques was found to be 0.91 angstrom. Let us now calculate the wavelength of the electron waves from these electron diffraction data. Above figure clearly shows that the phase difference between clearly shows that the phase difference between waves coming from adjacent scattering planes of crystal is given by 2 pi by lambda into 2d sine theta. Now for a constructive interference, we can write 2 pi by lambda into 2d sine theta equals to 2 pi n, or which gives lambda equals to 2d sine theta by n, where n equals to 1 to 3. This is equation 1. Now using above discussed experimental value, that is d equals to, that is a spacing 0.91 angstrom and theta equal to 65 degree and n equals to 1, we get the value of lambda using this value, which comes out to be 1.65 angstrom. Let us now compare this value of lambda with the corresponding value predicted by de Broglie hypothesis. The de Broglie wavelength of an electron accelerated by a potential v volts is given by lambda equal to h by p equals to h by in bracket 2m naught e to the power 1 by 2 equals to h by 2m naught ev into 1 by 2 equals to 12.264 divided by v in volt to the power 1 by 2 in angstrom. So for 54 volt electron, the value of lambda is given by lambda equals to 12.264 divided by 54 to the power 1 by 2 angstrom, or which come out to be 1.67 angstrom. Here we have calculated the theoretical value and experimental value both. And we compare these two values, they are very near to each other. So here we will notice that the agreement between the two values of the wavelength of electron given by equation 2 and 4 is remarkable. Within the months of the discovery by Davison and Germer, a British physicist G.P. Thomson also discovered diffraction effect with a beam of highly energetic electrons. In 1928, Thomson repeated his experiment by using platinum foil than the celluloid film. The diffraction rings observed with the polycrystalline metallic foil were found to be exactly similar to those observed for X-rays of the same wavelength as that of electron. This experiment of Thomson had provided even more convincing evidence in support of the de Broglie hypothesis. De Broglie was awarded with a Nobel Prize in Physics in 1929, and the same was awarded to Davison and Thomson in 1937. It is of interest to note that Sir J.J. Thomson was awarded Nobel Prize in 1906 for discovering the electron as a particle carrying negative electrical charge, and in 1937 his son G.P. Thomson also got the same prize, that is Nobel Prize, for establishing the wave nature of electron. With suitably designed experiment, the wave-like behaviors of a particle such as alpha particles, proton, neutrons, etc. has also been established.